Hello guys, we're going to look at section 2.4, the derivative. Now we've done the first half of this, so I'm going to go through pretty quickly, just a quick review, and then when I get to the new stuff, I'll let you know. So we started with looking at this notion of the rate of change. Okay, and so we said the average rate of change, if we're going from some x equals a to x equals a plus h, is given by this difference quotient here. Okay, and so remember the denominator, of course, is a plus h minus a, so those cancel, and that's why we just have h. And we don't want the h to be equal to 0, of course, because then I have 0 over 0, which is undefined. Okay, so this is a difference quotient, and we also talked about it being the slope of the secant line. So remember, visually, I want to know the change in my y. This is my y, which is from f of a plus h minus f of a, and then over my change in x. And we go from some a to a plus h. So that difference in between here is the h. And so that's this point and this point, the slope of that secant line. So the average rate of change gives us the slope of a secant line. So this is similar to the example we did in class, but slightly different. So we're trying to produce some widgets, and it's given by the revenue generated is given by this expression here. And it's true when I have between 0 and 20 widgets. So I want to know the production change from 9 to 12. So if I just want to know the change in production, that's this R of 12. Sorry, let's do this. We want to know this R of 12 minus R of 9. So we get $36. So what is that telling us in English? Right? If I produce from 9 and I increase to 12 units of this item I'm selling, my revenue will increase by $36. So the next question I want to know, not just the rate of change there, but what is the average rate of change? So what are we really asking? How much is it per unit change in X for each unit that I am increasing? Okay, so to do the average, of course, we do the change in revenue divided by the change in production. Okay, and so that 36 we got earlier, and then 12 minus 9 is 3, so we get $12. So on average, as we increase by each unit, it's increasing by 12. So this is per unit. So what we last talked about is, hey, let's talk about this new, what we call the instantaneous rate of change. So what do we mean by that? So if I look at this difference quotient, okay, and we want to get closer to some point A. So that's that same that A that's here. Okay, so our goal is, if I make h smaller and smaller, so this A and h are getting closer and closer together, okay, then the difference between the A and the h are so small that we're really finding out what's happening at this instant. So at this instant, this point is this point A comma f of a. And so what do we do now? We want to take the limit of this difference quotient. So taking the limit by letting that h get smaller and smaller and smaller is telling us what is happening at x is equal to a. So let's think about the visual interpretation. So assume that this h is equal to 1. What do we do here? If that h was equal to 1, it was the slope of this secant line. Now let's bring it in a little closer. Let's go to this point here. Then I'm going to get the slope of that secant line, assuming that I went through this point. Now let's get even a little closer to A. That's this point here. Getting slope of this secant line. So I'm doing this smaller and smaller slope until it's so close that I'm somewhere so close to the point A that I'm only going through my graph at one point. And when we go through a graph at 2 points, it's a secant line. But when I go through the graph only at 1 point, it is a tangent line. So now if we talk about this instantaneous rate of change, this is really just telling us what is the slope of the tangent line. We say at x is equal to a. So again, I want to know what's happening at this point. This point, that is my tangent line. We want to find what is the slope of this tangent line, which gives me the instantaneous rate of change, which we said is going to be represented by taking the limit of this difference quotient. So again, we have some a and a plus h. We want that h to get smaller and smaller, which means it's getting closer and closer to a. So it went from here to here to here till I'm so close that I'm only going through at one point, and it's the slope of the tangent line. So again, if we say the definition of the instantaneous rate of change, we can have this as a theorem that says, given a function y is equal to f of x, the instantaneous rate of change at x equals a is given by the limit as h approaches 0 of this difference quotient, provided that the limit exists. Okay? And we can interpret that value as the slope of the tangent line at a point A. And that point is a comma f of a. Okay. So we saw this limit as h approaches 0. We saw that this limit as h approaches 0, this difference quotient, we're going to give it a name because it's the slope of the tangent line, but we're going to call it the derivative. Okay? And so y is equal to f of x is defined as the derivative of f of x, and we're going to denote it by this f prime of x. So we write this f prime of x. Okay? And this is what we're going to call the derivative. So instead of saying the limit of the difference quotient, we're now just going to say the derivative. Okay? Now, if it exists, we say that the graph, not the graph, excuse me, it is a graph, but the function f is what we call differentiable at a. So we're going to use this terminology over. It's a function differentiable at a. Okay? And it's said to be differentiable over a particular interval if this limit or the derivative exists on some open interval AB. So it might not be differentiable everywhere, just like continuity, but if we can show some open interval that contains the x value we're looking for, we say it's differentiable over this open interval. So we have some different interpretations of this derivative. Okay, so we've seen these examples actually in all examples that we've done so far. Okay, we can think of the derivative as the slope of the tangent line at a particular point x. Okay, we can think of it as the instantaneous rate of change at a point x, what is happening at that instant. Okay, or we can think of it as that velocity. So that original problem we saw when the steel ball was being dropped. Okay, we can think of the velocity. So that limit of the difference quotient is also gives us the velocity at a particular time t. So how are we going to find the derivative of a? So finding the derivative, we're going to use what we call the 4-step process. Now, I will tell you that we can do all 4 steps in one, but we're going to go step by step when we do our first example. So the first step is we want to find f of x plus h. So evaluate whatever function is at x plus h. Then we're going to take that difference of f of x plus h minus my original function. The next step is we're going to divide by h. So this is that average rate of change. Okay? And then the last step is we want to take the limit of what we have done in step 3, and this is equal to my f prime of x, or my derivative of the function. So we're now going to find the derivative of this function. So what are we looking for? What is f prime of x? So step 1 says to find f of x plus h. So that means everywhere I see x, it's going to become an x plus h. So we have x plus h to be squared minus 3 times x plus h. Okay, so we do a little algebra and we get this expression here. Okay, we have to FOIL this out and make sure we distribute the negative amongst both of these terms. Now, step 2 says f of x plus h minus f of x. So we're going to take the f of x plus h that we found in step 1. So we have x squared plus 2xh plus h squared minus 3x minus 3h minus, what was our original f of x? X squared minus 3x. Okay. When I actually distribute this negative, this x squared is going to be x squared minus x squared. This is a minus 3x. This is going to become a plus 3x. So I'm just left with 2xh plus h squared minus 3h. Okay, so I think we stopped at step 2. We do some algebra. So step 3, we're going to now take what we took from step 2 and divide it by h. Okay, so when I take this step here and divide it by h, I notice that there's an h in common. So I could take out that h and I have 2x plus h minus 3 all over h. Okay, and I'm left with this expression here, 2x plus h minus 3. And step 4 says, step 4 says I want to take the limit of that distance quotient we have in 3. So that's the limit of now this new term here. Okay, and we have 2x plus h minus 3. We can just plug in, and I'm left with 2x plus 3. So what does this tell me? This says that the derivative of x squared plus 3x is 2x plus, it should be minus 3. So guys, let me erase this. Sorry. Minus, that's a minus right there, 3. So here's just what we've done. This is the math that we did earlier. We first did step 1, f of x plus h. And we got this here. Then we subtracted away our f of x. Okay, and we got this new difference here. We divided by h, and when I divide by h and cancel out the h's in common, I have this here. And now we want to take the limit. So step 4 says take the limit. So this is f prime of x. Now, let's recall that f prime of x is 2x minus 3. And what was one of the definitions for f prime of x? Is the derivative. So that's the derivative. It also gives us the slope of the tangent line at a particular point. So let's look at these particular points and see what that slope, what the slope would be. So if we do f prime of 0, 2 times 0 minus 3, it tells me the slope at at 0 is negative 3. F prime at 2, 2 times 2 minus 3. The slope is what? 4 minus 3, 1. F prime of 3, 2 times 3 minus 3, 6 minus 3 is 3. So this is the slope at x is equal to 0, the slope at x is equal to 2, and the slope of x is equal to 3. And these are the slopes of the tangent line. Okay, so here again, we find the slope of the tangent line of this function. We found the derivative to be this here. And so we plug in those values and we get the respective slopes. Let's see what this looks as a function. So I've graphed the function f of x is equal to x squared minus 3x. Okay? So keep in mind that the derivative gives us the slope of the tangent line at a particular x. So at x is equal to 0, this is the tangent line. Okay, and so that slope we see as negative is equal to negative 3. At 2, this slope is 1. At 3, the slope is 3. So notice it's negative here. Okay, it's positive here. Okay, and it's a little more steep here, so it's a larger positive number. So this is the information that the derivative is giving us, the slope of the tangent line. So I'm going to pause. I want you to pause, and I want you to find f prime of x, or the derivative of this, by using the 4-step process. Okay, so I want you to check to see if you get 2 minus 6x. So we're going to go through it quickly. First, we do f of x plus h. So everywhere we see an x, we plug in an x plus h, and we simplify. Once we simplify, we're going to subtract off f of x from that expression, and we should have this here. Step 3 says divide that by h, and we have this here. And then when I take the limit as h approaches 0, this term goes to 0, and I have that f prime of x is equal to 2 minus 6. Now, keep in mind, the derivative is dependent upon if this limit actually exists. If for any reasons we do this and my limit does not exist, we say the function is non-differentiable, okay? Or f prime of a does not exist, okay? And so keep in mind, if it does exist, we say that it is differentiable, okay? And if it does not exist, it is non-differentiable. So these are some places where a derivative may not exist or be non-differentiable. If there's a hole or a break at a, so of course if I have a function, I have a hole, okay, then it's not differentiable at this point. Let's call this a now. Then we won't find a derivative. Okay. If I have a sharp corner, so if I have a graph that has some kind of sharp corner, okay, some kind of point here, these sharp corners is not differentiable at that point A. Okay? Or anything that has a vertical tangent. So if I have a tangent line that looks like this, of course, the slope is undefined. Okay? And so since the derivative is the slope of slope of the tangent line, if the tangent line is undefined, then we will be non-differential at that point. So in summary, we found that the derivative of f at x, okay, and we're going to denote it by this f prime of x, is equal to the limit as h approaches 0 of this difference quotient if it exists. Okay, so how do we find out this value? Okay, we do this 4-step process to find this value. Now keep in mind, you can do this all in one step. You don't have to go through the 4 steps. This is step 1, step 2, step 3, and then step 4. But you can actually do this process all as one, as we've been doing in class. Okay, just find the limit of this difference quotient, and you still can find the derivative the same. We have now completed this section, and I want you to finish the homework for the section. This is, section 2.4, and we will look at problems when we return to class.